Hello, I'm Nicolas. I've been at Collabora for over a decade. I'm now principal engineer, specialized in multimedia. And my main interest and work on day-to-day is on GStreamer multimedia framework. But I also contribute to the Linux kernel through the Linux media subsystem in order to bring new API and new hardware support, especially hardware accelerators, which is a very good interest. So speaking of new API, I'd like to tell you a bit of the story of the apparition of codecs in the Linux kernel. Codec support isn't new, but it took a lot of time to stabilize and improve. So everything started in 2011. So in 2011, Google partnered with Samsung and Asus and actually produced the first ARM Chromebook. This Chromebook was based on Exynos 5 system on a chip, and it included an encoder called multifunction codec, the MFC decoder. And this was actually the first codec to be integrated into the mainline Linux. And this codec landed right on the launch of this device. Now, this type of codec that we later started calling Stateful codec, there was no terminology back then. How it works is basically that it has a coprocessor, whether it's a DSP or custom processor or ARM processor, doesn't really matter. But it has a coprocessor that will handle and manage the bit stream, parse the bit stream, and feed the required information, which is codec specific, to the accelerator. Of course, this is delivered to us as a black box, so we're only modeling what our imagination can see here. Now, they needed to fit that into the kernel. They didn't really have a subsystem, so they decided to pick the V4L subsystem and create a new type of V4L device, the memory-to-memory device, or M2M as a short. And in order to do that, they've used two distinct concepts in V4L. So V4L had actually devices that have queues, and those queues have specific properties. So one of the queue was the capture queue used for cameras, and the other queue was the output queue, which back then was used for analog output mostly, but could be used also for SDI output, but it's a bit abandoned these days. So they've decided to pick the capture as being the output of the codec, the decoded image. And then the output, and that's where it's a bit confusing, has been picked to be the input of your codec, so the bit stream, the encoded data. Of course, this was not enough. They also added the concept of enter queue configuration, because the selection of the codec will have an impact on which raw format you'll be able to support. Especially that some of these accelerators, actually, they offer also color transformation, scaling, or rotation functionalities. Now, just quick pros and cons. This type of hardware is relatively simple to implement in software. You don't need any knowledge, very advanced knowledge of the codec itself, because all the hard stuff is handled by the hardware. So you pass a bit stream and you get images out. Now, the downside is that to drive these accelerators, you need a firmware. And why it's a downside is because most of these firmware, actually all of these firmwares, are proprietary and are blobs, basically. So it's a piece of software that you actually upload to the card and you have no idea what it's doing. And this piece of software, as it manages your decoding session, may have some limitations. So there's a limit of resource on the chip to handle the stream. So even though you have very, very small stream, you might not be able to decode more streams in parallel with these chips. We even have implementation which only support one or two streams. So it's much harder to multiplex. So that's it. We had codec. In 2014, we had the second stateful codec being added, the CODA driver. So it was added for platforms called IMX.6 and IMX.51, which was still Freescale, which was bought by NXP later. And CODA actually is the name of the chip brand as manufactured by Chips and Media. So it's not a Freescale design, it's actual design that has been bought. This back in the days we didn't have any information about this this codec, so this was all reverse engineered by Philippe Zabel and his team at Pengutronics. Now, things didn't stay there, and Google wanted to go further, and they decided to partner with a new chipset vendor, Rockchip, from China. And with them, they created the second generation of ARM Chromebook, much more powerful, but it also came with a much more complex to use codec. Back then, in 2015, it was thought to be the Rockchip VDPU hardware. They didn't really know anything about the hardware, except what they had as a reference. Now, this new chip, the main difference is that there's no more coprocessor on the chip. So the accelerator are almost exposed as is. There's a bit of logic implemented in the hardware to make it kind of possible to use, but they're there. And instead of just having to pass the bit stream, you also need to pass the references and all the codec parameters needed to drive this accelerator. And the codec parameter, even though they're fairly standard, they need to be extracted from the bit stream. So they require deep parsing of the bit stream. And that's the easy part. You also need to understand the workflow, because some stuff is not encoded in the bit stream. Some stuff is deduced by monitoring the flow. And it's the case for references and many of the parameters. Now you may wonder, and you may have heard about GPU codec and the fact that these are also lookalike of the stateless decoder. So indeed, that's correct. So the GPU decoders, as found on Intel, AMD, and NVIDIA, are very similar. Instead of registers that you write into memory, they use actually a command stream. What happened is that the crafting of this command stream has been merged with the other commands on your GPU. And creating those command stream is something that have been decided to be done in user space. So it's hardware specific code in user space. It's a driver, but in user space, and notably through Mesa project. It would be pretty hard to implement a V4L driver for them, because we would have to copy some code from Mesa into the kernel, which is probably not where we want to go. In the end, what Mesa does is that it implements the command stream and expose well-known API like Intel VA API, VDAPU, which is now deprecated, and NVDEC decoder. On Microsoft Windows, they also have DXVA2, which is their GPU codec accelerator interface. Could we have done things differently? Could we have decided to expose these accelerator as a GPU? I believe we could, but there was a bit of a overhead of having to use one of those high-level GPU-centric abstraction layer. Now, how did they model this in the in the context? So they decided to build up on top of what was done for the stateful codec. So they still have an M2M device with a capture and an output queue, but now they add a lot of controls, and those controls are bitstream specific. Now the problem is that you don't just set controls to be applied on the next to be processed frame in the queue. You want to apply the control to a very specific frame in the bitstream. In order to do that, they created the request API, which is basically an object, a file descriptor, that you can pass when setting the controls and when queuing bitstream buffers. This basically, you could see it as if the controls and the buffers are now attached to the request. And then the request is queued and the driver will process requests rather than processing buffers. This way you can really associate the right parameters with the right buffer. On top of that, they decided to put this API in the media controller in order for that API in the future to be usable by cameras. And with the media controller came the topology. And the topology is kind of a really nice feature because there was a big problem of identification of your hardware driver, what your driver is doing actually with the other model. So the topology gives a very neat view of what your instance can do. Now, it will be really hard to understand all this without going a little bit over some codecs work. So I've picked up H.264 and I'm going to give you a little bit of information about H.264 itself. So H.264 bitstream is split into NALUs, so network access layer unit, something like that, and they form a sequence. And in this sequence, there's well-known types of NALU that will be found. So notably, the one that we really care about, the SPS, the sequence parameter set, are part of the parameters we need to pass to the IP in order to decode frames. The PPS, the picture parameter set. And then there's slices. Slices are visual bit of information, that the bit that you actually decode in order to create an image. And in these slices, there's a header, and we need to parse this header in order to do the bitstream processing. And for some accelerators, like the Allwinner CODA, we need to actually program these headers into the hardware, as the hardware won't parse it. It will just skip over. There's different type of slices. The IDR, the I slice and the IDR slices are slices that don't use reference. So it's per compression, a bit like your JPEGs or other images like this. And the DR in the IDR means that at this point, it's not allowed to actually, for the following frames, actually to use reference before this point in time. The P slice are slices that actually refer to frame that was presented in the past. And the B slice actually refers to frame that was presented in the past and that are going to be presented in the future. I use the term presented because the decoding order will be different from the presentation order. There's a reordering of the queue. Now, these NALU comes in two forms, in two packing. One is the Annex B NALU with a start code, which is nice for random access because you can actually locate the beginning of your NALU in the stream and start streaming. And there's another one, the AVCC header, which instead of encoding the start code, they actually allow encoding the size of the NAL. So you would read the size and jump over if you don't care about this NAL. So it's much faster to navigate, but you need to receive the data aligned with the NAL. So for storage, we will mostly use AVCC, and for streaming, we will mostly use NALUs in this case. Now, the decoding process isn't simple, and I'm just giving you another view of that decoding process. And this represents what you need to implement in user space. Fortunately, all this stuff is now implemented in Chromium, FFMPEG, and GStreamer. And assuming you have the luxury to be able to use one of these three, you won't have to program it yourself again. So, how does it go? So first you need to locate and parse the NAL headers. Then you need to parse all the non-VCL information. VCL is the visual coding, actually, the data that you're going to decode. So non-visual are informative NALs that are used in the process. And you also need to parse the headers of the VCL NAL in order to retrieve some information there. With this information, you'll have to calculate the frame number and handle the case there would have been some gaps, which happens in lossy networks. This, of course, is a recipe. So it's described in prose in the specification, and you just implement code out of the text. You also have to calculate the picture order count, the POC, and the picture number, which are numbers that will be used in some logic in the processing of decoding. So you need it for your code in user space, but the IP might need it for some logical. Now, there's two types of decoders. Some decoders will be frame-based, so you pass all the slices of a frame. So in this case, the decoder, the hardware, will have to parse the slice header, so you don't need to pass as much information. And there's those that don't do that, that will decode each slices separately. In that case, we need to prepare the reference list, as we will have to provide a very specific ordered set of reference as described by the specification. At that point, you got pretty much all the information you need for the next decode operation. You can fill the SPS, PPS, decode param, slice parameters, and pass that into a v4L structure format and set that to controls. If you're slice based, you need to apply another algorithm called the modification of reference list, which you picked from the reference that you created for the picture, and you transform them based on a per slice modification. And finally, you should be able to decode a frame. When a frame is decoded, you do your DPB management. DPB is the picture buffer, the displayed picture buffer. This is used to store your decoded picture and to figure out actually which picture are now ready to be displayed and which picture no longer have another picture that will have to be decoded, presented before it. Because of the B frames, the order of decoding can be complicated. So it's also a buffer to reorder your frames. On the v4L side, it's much simpler if we just look at driving the hardware itself. So on v4L side, you need to allocate a request. You need to set all the parameters. You need to queue your bitstream buffers for that request. You set the parameters for that request also. And then you queue that request, and instead of waiting for a buffer to come out, you actually wait for that request to complete. So you poll on the file descriptor of the request. It's a much simpler process than the other accelerator. And things stay there, and time passed. In 2016, we had yet another stateful decoder from MediaTek, actually provided by MediaTek. It was a bit annoying because it was limited to tile output, which support is still not great in the v4L framework. Then the year after, the Qualcomm Venus driver was merged also, and it's by far today the most featureful codec, as it supports MPEG-4, MPEG-2, H.264, VC1, H.26. What did I say? H.263. There's a typo on the slide. VP8, VP9, and HEVC to decode. And assuming you got the latest Snapdragon, I think it's 855 plus, you're gonna have all these encoders too. So MPEG-4, H.263, H.264, VP8, and HEVC. I suspect they most likely have VP9 also. So, as for our stateless codec implementation, development was pretty much stalled. In fact, it was not stalled, but it was blocked on multiple work in progress. So one of them was the request API. So it was hard to finalize the request API. It was picked up and renamed to job API. People didn't like the name. It came back to request API. And it took a while before this was finalized. And it was key feature in order to get this running. The other problem was that there was a very low knowledge of codec, how codec works in the Linux media community. So maintainers had to train themselves, find some times to understand how codecs works in order to review and make sure that the design was going to stay long enough. There was only one hardware running so far, the Rockchip 3288 VDPU. And there was just no formal specification to help focus on how these decoders are going to be used. And this stayed there till 2018, where really everything started launching. So Bootlink actually made a Kickstarter in order to finance the development of VPU support on Allwinner chipset. And with this effort, motivation came along. There was a lot of discussion in various workshops, and the request API was finalized. The MPEG-2 support landed in staging. H.264 was in progress, and the targeted user space back then was a VA API driver. So basically, you would use your Allwinner VPU just like you would use a VPU, an Intel VPU as an example. It was a good fit, considering that Cedrus, the driver that they created here, actually is a slice-based decoder, just like Intel produces. So in 2019, the crowdfunding was full steam, and basically things started moving. I forgot to mention, the crowdfunding was being developed by Paul Kosialski, an intern at Bootlin, and Maxime Ripard. So a formal specification was written. What's a formal specification? In the V4L, in the Linux media community, they tried to document how a driver is supposed to be written using the functionality in V4L and how it's supposed to work. This helped keeping drivers, it helps keeping the drivers more generic in order to run on various software without any difficulties. H.264, VP8, HEVC support was added with their controls. All these controls are not officially stable yet. They're actually staging, so if you want to use them, you need to copy the headers from the kernel, as they may have some modification later. Then things started to follow. On RK3288, the Collabora team actually started looking at finalizing Google upstreaming of that, and MPEG-2, H.264, VP8 was added, JPEG encoder was also added, and something special happened. So at that time, my colleagues were a bit overwhelmed by all this work. They didn't know much about bitstream. I was in multimedia. I had worked on the GStreamer parser a little bit, so I already had a good base knowledge. So I came to help and understand and review all these API in order to make this, to make all this work actually and make this proper. And as I was seeking for documentation on the Rockchip side and for other hardware, I was also in discussion with Chris Haley from Zodiac. Chris is well known for having pushed forward ETNAVIV reverse engineering project, the GPU driver called Viventi, for Viventi chip, that is found on IMX6 and now IMX8. And he was also behind CODA, pushing that codec forward, as he's using it at Zodiac in the infotainment system. And while I was discussing with him, he was presenting me his new IMX8M based devices, which was the new generation of in-flight entertainment there. And he knew back then that this new hardware from NXP didn't use the CODA chips to do the multimedia, and instead they had picked a design from Hantro company that was called G1 and G2, two different cores. So I was quite curious and I started searching for documentation. NXP is kind of nice because you just need to exchange your email and you get the documentation. So I started comparing the documentation of RK3288 and the IMX8M to my surprise, found out that they were not just similar, they were identical. The register set was binary compatible between the two devices. And then I came to my colleague and I'm like, I don't think this is a Rockchip design. I don't think this driver should be called Rockchip anymore. So just a little bit about Hantro. So, and why we decided to rename this driver Hantro. Hantro was a Finnish company that eventually got bought by Onto. Onto themselves got acquired by Google, and within Google, Onto developed the well-known VP8 codec that was one of the first royalty-free viable codec out there. It was not the first, of course. And then came VP9, which is highly used now on YouTube and everything on the web. Google didn't really want to keep that, but they did great work, as the Hantro team actually made a VP9 design, and that was made freely available to any silicon vendors. This business of hardware was then sold to VeriSilicon, who was still doing new revision of this decoding hardware. What we wanted to avoid, and that was something I had learned about just a couple of weeks before we found that this hardware was not actually Rockchip, was the story about STM-MAC. So STM-MAC is an Ethernet driver that is in the Linux kernel, and it is still called STM-MAC, even though the hardware is actually a designware. And it's not just a designware, it's the designware, the one that is used on most SBC out there. So that's very confusing when you first see that, but STM-MAC is actually designware driver, generic driver used across multiple SoC. And so we avoided to repeat a history mistake. The project continued, and we finally got more support from the community with the folks from LibreElect and CODEC, who came along and implemented this FFMPEG backend. So when we started, we only had the V8 driver, which was limited to Cedrus support, or the Chromium browser, which wasn't limited, but it's more complicated to do testing with a full-fledged browser. So they provided this FFmpeg support, and that actually boosted the development, as we could do faster testing and validation of our decoder. They also provided a lot of bug fixing in the driver in Cedrus. They implemented interlace content support, which we didn't have initially. And came 2020, everything was full steam. Support for the Rockchip 3399 came in with the RKV DEC driver, which is this time a Rockchip design. And something moved in GStreamer, so we gained generic base classes to do hardware acceleration decoding in GStreamer, something that FFmpeg had for years and years, which we didn't have in GStreamer. Instead, Intel, who was behind this development, decided to write some code highly specific to VAPI, and it was not possible to reuse this code. So Sung Ha, a GStreamer developer that was working at NavCorp back then, wanted to have DXVA2 support on Windows, and while doing it and while going through the reviews, he already had kind of split the bitstream generic part and the DXVA part, so I've asked him kindly if he could split that into base classes, which he did, and later I took those base classes and I made a new library within GStreamer called libgstcodec, which depends, of course, on libgst parsers, and it actually forms a very neat base class that we can share among multiple implementation. So we could easily see in the future to port actually the VA API stuff on these base class in order to share the bitstream work and enhancement that we do. On top of that, he implemented stateless support for NVDec, because NVDec property library offers both a stateful and a stateless interface. And it provides a little lower latency when you use the stateless interface. And then, beginning of the year, I implemented GStreamer support for H.264 and VP8 decoder, and it actually landed upstream. I guess it's much easier when you're the maintainer of such a subsystem in GStreamer. But it was a nice addition also to our testing workflow, as GStreamer opened up other ways of using and testing the hardware. All this was targeting, I was racing this, and I was targeting the Embedded World Conference, and I was supposed to do a demo there. And we actually managed to get this all in time until COVID appeared and they canceled the show. So I never got to show the demo that we actually had prepared. And then, now that we had FFmpeg support, Chromium support, and GStreamer native support, it was commonly decided that there would be no more work done on the VA driver, as it was not very relevant anymore. There's, of course, a lot more to come in 2020 at 2-meter distance. Now, all this work enables codec, the hardware decoding support on many interesting projects, and I only picked 3 of them, but there's more, of course. And interestingly, the MNT Reform laptop, which is a fully open source and blob-free laptop running mainline Linux, is based on IMX8M, which has one of the supported decoder. In the middle, that represents the Pine 64 phone, is an Allwinner 64 chip, which is supported by Cedrus. And on the right, the Purism phone, the Librem 5, running some GNOME stack, actually, and using GStreamer actually gain the ability to do hardware decoding. So quite a win. And now it's going to be showtime. So, in order to demonstrate all this, I have chosen the LibreComputer Tritium, because I really like what LibreComputer do. They provide a wide variety of chips that have the potential to be fully supported mainline or are already fully supported mainline in very simple packages like this. In this case, it's a Allwinner H3, and we're going to demonstrate the CODEC driver. In order to do that, I brought a little HDMI recorder from a company called InnoGenie, one of the rare French-Canadian hardware company I know. So I'm going to plug HDMI in there. As I'm doing TFTP NFS booting, I'm going to put Ethernet. And finally, I'm going to boot it up. Oh, I'm going to show you the console. And I'm going to boot it up straight from my laptop power. And hopefully, that's going to work. Oh, I've also connected a little keyboard so I can actually log in and type. So now it's booting. So in this case, my NFS root is Fedora running in the background. It's running head of Linux TV 3 with one of the patches I've submitted upstream. So I'm going to log in. Voila. And I'm also going to run the latest GStreamer, actually from yesterday. And I'm going to use it, what we call uninstalled. So I'm using GST build to build the integrity of GStreamer, to cross-build the integrity of GStreamer for the platform. And this command, gst uninstall.py, will actually set up an environment so the plugin can be used in place without being spread out. It takes a little while because there's a lot of path and the paths are getting big, but it will get there. And NFS is not helping, of course. Now as a media player, because I don't have any graphical setup in there, I'm going to use GST Play with KMS Sync, and that's going to go on the video overlay plane. But that plane is normally in the background. It's an underlay on this device and on most modern devices. But this hardware has this nice capability that you can change the Z order. So I'm setting Z pos to 2 to bring it at in front, so you can actually see the video. And in the video itself, it's coming, it's pre-rolling. I'm actually displaying, let me pause here, the demo that we had prepared for Embedded World 2020. On the left, that's the monitor of the streaming server, which provides streaming transcodes in various formats, SRT, REST, and HLS. I'm not going to go into these, that's not the goal of the day. And on that screen, it's actually an IMX8M evaluation kit running the demo. And then in the back, this little device here is the Zodiac. It's the upcoming actually Zodiac and for entertainment system for planes that is under development. And we decided to demo some touchscreen capabilities and some underlays capabilities that is made possible. It's actually a mix of underlays and GPU rendering on this device with smooth hardware accelerated decoding. And that's it for the demo. Hope you enjoyed. And on that, if you have any question, you can place your question into the Inspo system and share with us. I will try to insert as many as possible. Thank you for watching. Thanks for Collabora for making this presentation possible, and enjoy your summer.